welcome back. Thank you very much. Today's talk starts from this observation that, as we know, in complex systems, a crowd of intelligent individuals is not necessarily an intelligent crowd. And why? This is because the sum of many individually, let's say, good or optimal choices may have unintended negative outcomes. This is, a wonderful example of that is the famous Schelling segregation model. If everyone wants to move in a city, so to optimize the homophily, in the case of Schelling by race, but in general, the homophily with other people, at the end, everybody will be happy, but the city ended as a segregated city. So optimal at individual level, not optimal at the collective level. Why? Because choices influence and interfere with each other on top of shared resources. Now, we have to say that within this complex situation, there is yet another ingredient, which is AI. Actually, all the choices that we do are nowadays suggested, recommended by assistants and recommenders that I will call AIs for short. And so at social this can be an issue because of the uniqueness of this kind of social technical systems. Indeed, AI generates what we can call a feedback loop. So in other words, users' preferences, in social media, whatever, they determine the training data on which AIs are learned. But then AIs influence back users' preferences and decisions, which are then used again to make the retraining. So this is a feedback loop. And this feedback loop can clearly determine impactful changes in networks, in complex systems, but actually in many contexts, we still ignore how. Let me provide you a couple of examples. The first one is, let's say, social media, public discourse, and also markets diffusion of opinions. That is, the diffusion of opinions and financial decisions are influenced by AI, and we know from several empirical, simulative, and interventional works that recommendation on social media may artificially amplify radicalization, echo chambers, filter bubbles, and so on. Similarly, profiling and targeted advertising may further increase inequality and monopolies and perpetuating other non-desirable situations. Another example, a bit less explored, and this is the example I want to deepen today, is human mobility. So when we explore a city, nowadays we use Google Maps, Waze, whatever. That is, we use AI recommendation to reach the place. For example, I reached this place thanks to the suggestion of Google Maps. But navigation apps may create chaos if all the cars are driven to the same path. That is, an eco route is not eco anymore if we all go through that route. A similar example is the example of what we call in Italian partenze intelligenti. If we want to avoid traffic, but we all start at the same time, that smart start is not smart anymore. Okay, so I want to provide you an example of an experiment we did, trying to understand this insidious triangle in which we have, on the one hand, mobility demand, that is the OD matrix specifying where people should go. For example, how many people should go from here to the station and back. Then the AI suggestions and how this dialogue between the two influence some outcome that can be the congestion in the city or, for example, the amount of CO2 produced by the vehicles. So just to motivate further why this is interesting, I want to tell you the story about this city, Leonia, which is just an anonymous city in the countryside of US. But you can see that this city in New Jersey is surrounded by this highway. So it happened in 2017 that there were some heavy works in the highway. And so people started the AIs to suggest an alternative routes. So all these AIs, Google Maps, Apple Maps, Waze, whatever, they suggest to go through the very small and hilly streets of Leonia, creating such a congestion that people, residents in Leonia, were not able to go out of their home. So the city was completely blocked. Clearly, this is an extreme case, and although this extreme case is not isolated, because we can document many of these cases, it is still, worth investigating what can be the impact of these AIs on the urban environment. What's the situation now? The situation is that actually we don't know what the impact is because existing results are incomplete and contradicting. For example, for some cities, they say that Google Maps or similar, they may reduce CO2. In other cities, they observe that it may increase. In yet other cities, they observe that maybe they can decrease CO2 but increase NOx, which is dangerous for human health. So we miss up a complete mosaic of what this impact is. And here you can find some papers when they try to do that. What's the problem here? The problem is that in order to understand what is the impact, we should be Google Maps, Apple Maps, Waze, and so on, but we are not. At least I'm not working from them. So how can we try to understand? With simulations. So we do what-if analysis, and hopefully, if we do it in a right way, we can understand what is this impact. And this is exactly what we do. So we develop a simulation framework to understand what is the impact of different navigation services or in terms of CO2 productions. So our assumption is that different navigation systems may suggest different paths given the same origin destination. To convince you about that, look at the example on the right, where we have an origin and a destination, and we queried 4 APIs, the APIs of 4 different systems, and as you can see, we obtained 4 different paths. This is why the navigation services have different algorithms to estimate this path, different view of the road network, and so the results is not necessarily the same. It's the same at parity of OD for a given service, but it may vary across different services. Okay, this is the framework. So we select a city and we download the road network. Now road networks are freely available on OpenStreetMap, for example. Then you would find some mobility data to estimate the mobility demand, which is a matrix saying how many people go from this position to this other. Then you sample some trips from this origin destination matrix. So you obtain n, let's say 10,000 origin destination pairs. Now you have to suggest a path to reach the destination from the origin. And this is where navigation services come into play. So we query APIs, public APIs of different services to obtain this path. But then these vehicles are supposed to travel all together within a city. So in order to simulate the fact that they travel all together, we use a simulator, a traffic simulator, Sumo in this case, which is, first of all, open source, and then it is known to be pretty good. It has some limitations, which are also well known, but it can simulate, for example, what happens when cars meet at crossings, when there are traffic lights. They simulate also accidents and so on and so forth. It's pretty realistic. There is an entire literature on how Sumo can be used for that. Finally, we do the simulation, and what we collect. We collect several information, but just let me focus on CO2 emissions. There are specific equations that can be used to compute CO2 emissions from the GPS-like trajectories that are the outcome of these simulators. And so we study whether or not these CO2 increases or not. So this is a summary of the framework. We focus on 3 cities for now, which are Florence, Milan, and Rome, which are pretty different both in size and network density. You can see that Rome is very, very sparse, for example, compared to the other. And then we select these systems, which are Google Maps, Mapbox, Bing Maps, TomTom, and TomTom Eco version, which is supposed to provide you ecological, respectful, let's say, routes. There are some other services whose API are not available. For example, we couldn't find public APIs for Waze or for Apple Maps, so we cannot test them. But maybe in the future they will be available and we include them. Then how to simulate what is the impact? So if these services had no impact, so if people follow or do not follow this kind of suggestion, the CO2 level should be the same, let's say. But if otherwise, if there is an impact, so if we increase the percentage of vehicles following this suggestion, we should expect some CO2 to increase as well. So this is what we do. We vary the percentage in the simulation of people following the suggestion from any service and see what is the resulting CO2. This is the result we obtain for Florence, Rome, and Milan. So on the x-axis, you have the increasing percentage of people following the suggestions, and on the y-axis, you have the CO2. So you may see that regardless the service and also regardless the city, when you increase the percentage of people following these navigation apps, there is an increase in CO2. So the impact is not negligible. Otherwise, it would have been something like flat, let's say. Okay. Then with different patterns based on the navigation system and on the city, the pattern is seemingly linear in Florence, maybe super linear in Milan. It depends on this is something that we are still trying to make more formal. So why this happens? So one hypothesis is that what you do, what navigation services do is to foster conformism, a conformist behavior. Because since for the same origin destination, exactly the same suggestion is provided, so all people follow exactly the same path without any variation, in a sense. So this means that if we increase the percentage of people following the suggestion, we use less and less available paths. This concentrates people on the same path, and so this could be one of the reasons why we have an increased congestion and consequently CO2 emissions. In order to test that, we computed how the number of total traveled roads changes by increasing the percentage of these navigation services. And indeed, the higher the percentage, the lower the number of traveled roads. This means that the more we follow this suggestion, the less roads we touch, and so the more concentrate on a few roads. Here, for example, we have an example on Rome. A GIF that is not working, I don't know why. Because it's a PDF, of course. So I forgot to. It's a PDF. It cannot work. Anyway, you should see that by increasing the percentage of people following the suggestion, the enter become empty because we use less and less roads in a sense. Okay, so recap: the higher the percentage of vehicles, the higher the impact, and this is true everywhere, regardless the city and navigation app, with different patterns, depending by the city and the navigation app. So the question is now, how can we face this conformist behavior? Well, the answer is pretty probably trivial. We can face conformism with the opposite of conformism, that is diversity. So we can artificially inject in this suggestion some randomization so that we force people to diversify more the paths. So we developed an algorithm for that. I don't want to, to provide the details. You can find them in the paper. But, the interesting thing is that if we do that, actually, for some situations, we are able to nullify the impact of the navigation services. In other words, if I take the suggestion from Google Maps in this case, and I randomize it with the specific parameters, then instead of increasing, we obtain a seemingly flat behavior. This is true for Milan and for Florence, not for Rome. Still, we are still in the phase of understanding why Rome is a mess. Intuitively, we know why, but scientifically, we don't know yet. Because in Rome, we can only mitigate the impact by randomizing, but we cannot entirely solve the problem. We are now studying in detail what is the structure of the road network of Rome in relation to the structure of the mobility demand to understand whether or not we can predict the functional form of this, perturbed algorithm. So at the end, we have only actually 3, not 2 cities, but we simulate 1 hour only for computational reasons. We are trying to fight against the machines to understand how to extend to several hours, but we did it for 1 hour, but in different phases of the week and of the day, and results are pretty consistent. So we expect not to change very much. Then there are some questions open. The first is, how much we can diversify in a city? It seems that in Rome, we cannot diversify so much, or in other words, diversification is not so beneficial. This can be because in Rome there is not much to diversify, or for other reasons. This is an open question. And what about other contexts? That is, if the hypothesis that it's the conformist behavior that generates this non-desirable outcome. So what happened, for example, in online retail, in the recommended used by Amazon or whatever? Do they force a conformism as well? And how does this conformism generate non-negligible impact, and how can we solve it? And also we are doing some experiments on ChatGPT, because of course it is a wonderful tool, but is likely to probably standardize the way we write text. So we want to understand to what extent these kind of foundational models, large language models, can create conformism, and eventually how can we diversify them and maybe making them distinguishable from human generated text. That's it. This is the team of people that are doing the work, and that are summarized in these two papers of past year. Then is yet another paper in coming, and that's it. Thank you very much. If you have any questions, I will be pretty happy to answer. Thank you.
A question? A question? Comment? Marks?
I have a question on a detail. So the first time that you show the three situations of Florence, Rome, and Milan, there is something bizarre on Rome. Yes, this one. So with these two models, the violet one and the circle one, at about 75%, there is a sort of saturation, and then it goes down again. So I wonder whether this is because at that point people just couldn't move and abandoned their car by foot, or just walking, or why is it possible that by increasing the traffic, the CO2 goes down?
Thank you very much for the question. Actually, these two navigation services are Eco TomTom and TomTom, which is pretty similar to Eco TomTom. So TomTom, the not eco version is already a bit eco. The eco is a further. So this seems that, and this is interesting, that eco routing services like Eco, TT, and TT, they are better than the others. Indeed, you can see that at a given point, you can decrease the CO2. Of course, the CO2 is still much higher than the base case in which you don't follow, but that decrease. What does it mean, in my opinion? It means that on the one hand, eco-routing, at least regarding CO2, they are better because they try to make you follow a seemingly green route. But on the other hand, an individualistic perspective is not enough to have let's say, a significant reduction of CO2, because we have to take into mind that these services aims to provide you, to satisfy the user. So they aims to provide you the best route for you, not the best route for a combination of people. So even though they are a bit better, as we can see, still the CO2 increase up to a certain point. Then why for Rome there is this kind of hyperbolic, parabolic behavior, and we don't find it in the other cities, is an open question that we're trying to answer. Thank you.